Alright, so, here we go. So, why are quasars cool if you're not already convinced that they're just interesting in their own right? Why scientists want to study them is because they are so bright, they're some of the most distant objects that we can possibly see. They produce so much light that we can see them even though they're really, really far away. There we go. Because they are so distant, right, they're some of the oldest objects that we can see. So because light takes a finite time to travel, when we see light coming from things that are so far away, we're actually seeing them as they exist such a long, long time ago. Okay? And because of that, it gives us a key into what the universe looked like when it was much, much younger. So by studying quasars that are so far away, you can get a picture into where the matter was at the beginning of the universe, what galaxies looked like that long ago. Okay? So that's why scientists are interested in them. So this project that I'm working on right now is not looking so much into the science behind the quasars, but how do we find lots and lots of them to study? How do we find as many quasars as possible in the most efficient way possible? Okay? So first I'm going to talk about the traditional way that you identify quasars and verify what they actually are. Okay? So starting out with spectroscopy. So you're measuring the intensity of electromagnetic radiation at specific wavelengths. Okay? So if you have light coming into a prism, you divide it up into all its parts, and you measure the intensity at lots of wavelengths. Okay? So that's the basic idea behind that, and we use that to look at the specific features of objects in the sky. Okay, so here's one for the sun. Okay, so mostly you just have flat across most of the way, right? But then you have these dips at very specific places. So all the light produced inside the sun comes out, and you get across the top here. And then these are different things in the atmosphere of the sun that we can identify. So hydrogen and helium. These key us off to what exactly is in the atmosphere of the sun, things that are absorbing the light coming out of it. Okay? You can also see it here with all the different colors, right? So we have the blue light over here, and here's the keys to what is in the atmosphere of the sun. Okay? So that's what a typical star looks like. Okay? Any questions so far? Okay. So here is what a quasar spectrum looks like. It's very different. Right, so we have pretty much the continuum across here where it's pretty flat, but instead of having those absorption features from the elements in the atmosphere of the sun, instead here we have specific peaks that key us off to what is happening inside that quasar. Okay? So it was initially looking at these that kind of surprised scientists. This is something weird happening. We've never seen anything like this before. Because where these lines were, the peaks here didn't correspond to any elements they'd ever seen before. So what's happening inside these quasars? Okay? And so that's how we identify a quasar, is by the specific spectrum that we get out of the telescope. Now, the reason that it surprised scientists what they were seeing here in the spectrum, where these lines were in a really weird spot, was because they didn't expect these objects to be so far away. Now what happens when an object is really far away is that it gets redshifted. Okay, so the lines that were initially here, if the object's very far away, get scooted towards the red part of the spectrum. Okay. And so these lines that they saw, go backwards. So, there we go, were not in the spots where they expected it. They were all shifted to the right, because the objects were so far away. And that's what surprised them. And that's what first gave them the idea that maybe these aren't stars that are just weird. Maybe they're objects outside of our own galaxy that are very, very far away. And so this is what we're looking for when we're looking for a quasar. But one of the problems with spectroscopy is that you have to look at each and every object individually. Spend time on your telescope to look at each and individual one. And quasars are very rare. So odds are if you just start picking random objects out of the sky, you're going to waste most of your time and money. Okay? So to save time, we use another method called photometry. Okay? This one is much simpler. You just point your telescope into the sky and count the photons that are coming into it. Okay? So we have CCD cameras and telescopes, much like a regular camera, except much bigger. And the light coming in, you just count how many photons you get for each object. Okay? And so if you just count all of them, then you get an idea of how bright the object is. You can also look in just a specific band of light. So I want to count all the photons coming in that are basically red. I want to count all the photons coming in that are basically green. All the photons coming in that are a little bit infrared. And you can look at the different bands of light coming in. Okay? And then compare the two to get an idea about what sort of object you have. Okay? So this is the telescope that all my data comes from, Sloan Digital Sky Survey, and these are the different bands that we look at. Okay, so this one here, that's green, this is the ultraviolet band. The Y scale here is just how good a filter that is, how sensitive it is. So this one is not very sensitive, but when we're looking here in the green filter, which we call the U band, we're looking at all the ultraviolet light. Okay? If we're looking here in the blue one, we're looking at all the green light. Okay, so this is pretty much green light through here. This black region here, this is all the red light coming into the telescope. We call this the R. And the red line here is the near infrared region. And the purple line here is the infrared region. Okay, so we have 5 regions of light that we look at. And each object we look at in all of these filters. So we have an idea of how many photons are coming that are this color, how many photons are coming that are this color, how many are this color, how many this color, how many are this color. So we look at every object 5 times in each of these bands, and it's much more efficient than going through and taking the spectrum of each individual object. So we can look at the whole sky at one time, look at lots of objects in each of these bands. Okay? So when we talk about the color of an object in astronomy, we talk about the difference between 2 of these bands. So I have 4 colors that I can look at. I have the U minus the G. So this is how many photons I get in the ultraviolet minus how many photons I get that are green. And this is how many photons I get that are green minus how many photons I get that are red. And so I have 4 colors in that way. So it's not color in the traditional sense that you think of, but this is how we define a color. So I have the U minus G color, the G minus R color. And that's just a difference in the brightness between those 2 bands. So if this number that I get coming out is positive, that means that this object is more ultraviolet than it is green. If it's negative, it means it's more green than it is ultraviolet. And the same for each of these. Okay? And so if I look at each of those for my quasars, and I look at each of those for my stars, I get different values, and that's how I can distinguish the 2 of them. And it's a much more efficient way than taking the spectrum for each of them. Because then I can look at thousands and thousands of objects and see where they live in these different colors. So along this axis here is the ultraviolet minus the green, and along this axis here is the green minus the R. The blue dots and the blue lines represent where the quasars are in those colors, and the red represents where the stars are. Okay? So this is where my quasars are in general, though they span this whole region, and this is where my stars are. So they span this whole region. Okay? So typically what is done is I would draw a line through here and say, and maybe through here, and say if my object is in this part of that color diagram, it's more likely to be a quasar than a star. Okay? And then I'd look at this next diagram and say, here's my green minus my red, and my red minus my infrared. This is where my quasars are, this is where my stars are. And I could draw some sort of line saying, like, okay, so if it's in this part of this diagram, then it's more likely to be a quasar than a star. And I could go through and do that comparing all my different colors. And then if I had some new object that I took the colors of, I could say, okay, so given these colors, is it more likely that it's a quasar or a star? Right? And then if it's much more likely to be a star, then I wouldn't waste my time taking a spectrum of it to verify. Because it's probably not worth all those hours on the telescope. And that's what's usually done. That's the methodology used at the Sloan Digital Sky Survey, where this data came from. Okay? Now what I'm looking to do in my project is to develop a method to find quasars more efficiently. And I'm working off of some code written by my advisor back in 2004 that, there we go, kind of does this using very complex statistics and computing. So I'm going to walk you through the steps, and I made lots of pictures that are kind of fun to kind of show you how this works computationally. Now the code is actually written by computer scientists, and so I can't even read it, but it does work very, very fast, which is impressive. So we'll go through this together. So a few terms that you need to know before we start. Training sets are samples of known stars and quasars. So these are all objects that spectrums have already been taken from, and we know precisely whether it's a star or it's a quasar. Okay? In the computer, the quasars are zeros and the stars are ones. By star, we mean everything that's not a quasar. So a star could be a galaxy. A star could be anything that's not a quasar. We just call them stars because most of them are stars. Okay? We have a set for the stars and a set for the quasars. So there's two training sets. And what they do is they go into the computer and teach the computer what we're looking for. Okay? So you train the computer that this is generally what a quasar is, and this is generally what a star is. Okay? And we have a test set, which is all the unknown objects that we want to classify. And this could be anything. And we take these in one at a time and ask the computer, given what I told you in my training set, is this object a quasar or a star? Okay? And the name of the software that does that, the code that does that, is the non-parametric Bayesian classification using kernel density estimation. But we just call it NBCKDE. Okay? Those words do mean something, and we're going to start out by talking about the KDE part. So this is the kernel density estimation. Okay? And I put the equations up there because they look pretty, and because I'm learning how to use this new presenting stuff, and it lets you do typeset equations, so it's fun. But we'll walk through it pictorially. And Mitchell, yeah, I'll let you look at the slide after. Okay? So using the kernel density estimation is much like doing a histogram. Okay? We're building a probability density function, a function that tells you how probable it is that the object's a quasar or a star based on some position. And position, I mean color. Okay? So this would be U minus G or G minus R along here. And each of these little dots is one of my quasars or stars, and I represent its position by a histogram. Okay? Now this is really basic, a really good way to think about it, but computers don't like histograms, right? Because I have vertical lines here, incontinuities, gaps in it. Okay? And it only tells me exactly where the quasar is, and doesn't take into account that there are errors in my measurement of the magnitude or things like that. So instead of representing each object just by a bar on a histogram, instead I represent it by a Gaussian or a bell curve. Okay? So at each of my objects, I just put a little Gaussian where it is. So each of them have a little curve, and then I add all those curves together, and I get this. So this tells me if I had some other unknown object, and it had a color right here, it's very unlikely that this object is like these other ones, right? But if it was right here, then it's very likely that this object is of the same type as the others. Does that make sense? So this curve tells you how probable it is that there's some of those objects like that at that spot. Now it's tricky. One of the things we spend a lot of time doing is figuring out exactly how wide to make those Gaussian curves. So if I have it like this, where they're very wide, I lose some of the details of my information. Right? It's very smoothed out. But if I make it like this, then maybe I'm getting some artifacts that aren't actually real. So just in the same way that you need to be careful how big or how small you make your bins in your histogram, we have to take into account what we call the bandwidth when we're doing it to make sure that we're not creating things that aren't there or losing information. And that's really tricky. Now, this is doing it for a single color, right? I have my ultraviolet minus my green color here, and I have my probability. What we do in the computer is do it in 4 dimensions at the same time, and we get our probability distribution. So this is what it looks like in 2 dimensions. So each of my little objects are here, and say this is one color, this is the other, and the height of this peak tells me how probable it is my object is of the same type as that. So I make one of these for the quasars and one of these for the stars, and have them in the same space, and then I can take my unknown object and place it there, and figure out how probable it is that object is a quasar, and how probable it is that object is a star. Okay, so I put it in here, at, here we go, at whatever spot it belongs, and measure the height of my probability distribution function. Ask it how probable it is that it's the same time. Okay, so measure the probability of the star and measure the probability of the quasar, and get out some number from that function. And that's the KDE part of the code. Okay, that's the first part. Any questions about that? Okay. If anybody can visualize it in 4 dimensions and explain it to me, I'll give you $1. Okay, so the second part is the NBC part. Okay, so that's the non-parametric Bayesian classification. Okay, so this is where we talk about some fun probability stuff. Okay, so right here is where we stick in the probability from the KDE of it being a star, here and here, and here's where we stick in the probability of it being a quasar. Okay, and these little pieces here are what make this Bayesian classification. That's what we call the prior. Okay. So if we were just asked if it's a quasar or it's a star, we could ask the computer, right? The computer doesn't know anything about the real world, like the scientist does. So we ask the scientist to make an educated guess, your prior belief that the object is a star. And that's some number between 0 and 1. Okay? And so say that 5% of the objects up in the sky are quasars, then we tell the computer that the prior for the star is 0.95. 95% of the objects should be stars, and 5% should be quasars. So that just goes in here to weight these probabilities. We weight this one by 0.95, and this one by 0.05. And that's how we weight them based on what our understanding is of the real world, what's actually up there in the sky. Now, an easy way to think about it, I think, is how did you scale those relative curves, right? We would scale the probability density function for the quasars down to 5/100ths its normal height, and leave the other one at 0.95 its normal height. So the quasar function is much shorter than the star function, because stars are much more common in the sky. So then we go and do the actual classifying. So if our probability function, our Bayesian, spits out a number above 0.5, that object is a star. If it spits out a number below 0.5, that object is a quasar. But we can do something better than that, really, because we get out the raw number, right? So if it spits out a number of 0.999, we're very, very certain that that object is a star. If it spits out a number of 0.001, we're very certain that that object is a quasar. So we don't just get out some binary classification, we can actually get out some information about how certain we are about that classification. And so we make our catalog of objects, we make those numbers available. And when the scientist actually goes to put together a data set to do a study, they can decide whether or not they want a very, very pure sample of quasars. They only want things that they're very, very certain are quasars. Or maybe they want a very complete sample that has some contaminants in it of stars or galaxies. So depending on how large a data set they want and how willing they are to have impurities in it, they can decide how many objects to include in their study. So that's the cool thing about this. Everyone feel like they kind of understand it? Does that make sense? Okay. So here's some results that I've done to kind of check how well this algorithm is working. Okay? So this data set has about 12,000 stars in it and about 9,000 quasars, all of which are spectroscopically confirmed. And what I did here is I removed a single object. So I removed one star, built my probability distribution function, built it for the quasars as well, and then used that minus the one object to classify that single object and see whether or not the system classified it right. And I went through and did that for all 17,000 objects. Or I told the computer. And so this is how well it did. So the red objects here are the stars, and the blue objects are the quasars. This is my color ultraviolet minus green. This is green minus red. This is green minus red. This is red minus near infrared. Okay? So out of those 9,000 quasars, it classified all of them correctly except for 176 that it classified as stars. And then out of all the stars, it incorrectly classified 37 out of 12,000 as quasars. So that's about 99% accuracy, which is leaps and bounds better than drawing your boxes on your diagram, right? And besides that, you also get an understanding of how confident you are in the classifications when you classify objects you don't know about, okay? And these ones that are incorrect are mostly in this area where they overlap. Now, unfortunately, those are the ones that there aren't very many of that we know about, and so it's harder to classify those. And we were working on different methods to correctly classify those ones in the region where they overlap. So any questions? Does that make sense?
Tina,
yeah.
Would you, could you set a limit to make it pure in a sense? The ones that were misclassified, were they with low confidence also? Or,
No, all of, you mean in the algorithm?
Yeah,
yes.
It came out, so they came out.
They're ones that are like
yeah.
0.55 or 0.45. They're right on the edge. So if you were to say, I only want a very pure sample, so only like a couple of those would actually get included. Yeah. It's the ones that are like here and here that are very far from the star distribution that get classified with a very high certainty, and then the stars that are up here and up here that get classified with a very high certainty. Any other questions? So I have some more time to talk about the additions to this that I'm making. So this is something that's been done before by my advisor. Now with this data set, the catalog that's coming out of here we're going to publish in a little while. This is new data, that's why there's no like citation on the bottom. But what I'm working on for my thesis is adding in some new information other than just colors. Colors aren't the only thing that distinguish quasars from other objects in the sky. So a couple things we're going to talk about are variability and astrometry. These are new parameters you can add into the classification. And hopefully, if everything goes well, we'll have color, variability, and astrometry all at the same time classifying the quasars. So instead of having it in 4 dimensions, you'll have it in 8, where you have 2 parameters that describe how the object varies, and then 2 parameters describing the astrometry. So I'll tell you how we measure those. So a quasar's brightness changes over time in a very distinct way. So on here you have time along the bottom and brightness going up. Right? Each of these little points show the brightness over time. So it kind of dips and changes. And most stars remain fairly constant. Some change in a very periodic way, but no other objects in the sky changes in the way a quasar's brightness changes. Okay?
What's the time scale on that?
This is 2,500 days. This is 2,000 days. So this is less. This is like about a year. Yeah, this is several years across here.
Tina, is that periodic over long periods?
It's stochastic, actually. in general. It looks like Brownian motion,
All right.
which is kind of weird. Yeah. Okay, so we describe the changes in brightness with just two numbers. And how we do that is, oh yeah, there you go, Carl. With a semi-variogram. Astronomers often call it a structure function, but statisticians call it a semi-variogram, and geologists often use it actually to figure out where to mine, which is weird. And they also call it a semi-variogram. So you look at the differences in magnitude of the quasar as a function of the differences in time. And so in this way, you don't have to worry about when you started taking your measurements, when you finished taking your measurements, maybe you're aliasing something by accident. There you go. This gets rid of all that. And so there's an equation here for it. But let's look at the picture here. So what you do is you take every possible pair of points. Okay? So say you look at this point and this point. You measure the difference in time between those two observations. And then you measure the difference in magnitude between those two. And you do that for every possible pair of points that you have data for. Okay? So you look at these two, they're about 1.5 years apart, and a very small change in magnitude. You look at these two, and they're about 1 year apart, and they have a larger change in magnitude. And you go through and do that for all possible points in your light curve. So right here, this is whatever time you're looking at. You get the magnitude, subtract from that the time here, you square it, add them all together, and the squaring gets rid of the sign, and then you divide it by 2 because you accidentally count all the pairs twice. And you get this function here. So what that looks like is this here. So this is a light curve at the top. It's actually generated by a computer. That's why you have so many points. And this is the semi-variogram. Okay? So the trend that you get is that very small time steps, you have very little change in the magnitude. The changes get bigger and bigger as you get at larger and larger time steps, but eventually it levels off at some characteristic change. Because the quasar doesn't in general get brighter, 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 or dimmer, 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 it just changes randomly. So once you look at bigger time steps, you can't get larger changes in magnitude than the region that it stays within while it's varying. Make sense? So it goes from here to here, but it doesn't in general get brighter or get dimmer over time. Okay? So this kind of describes that. Now what we do to characterize the variability with just two numbers is fit this with some sort of function, right? And this is where things get tricky, because no one agrees on what sort of function you should fit this with. Some people say that it's Brownian motion, that's the general convention. A grad student that I work with at Drexel, his mission for his thesis is to prove that wrong. So he says that you should fit it with some sort of logarithmic thing or something. And there's just not enough data on it yet to determine. We can't get this interval over here very well in very short time scales, and telescopes haven't been good enough for long enough to get the data to fill out this side over here longer than several years. So figuring out how to characterize the variability with just those two numbers is something that we're working on to be able to add this to how we classify the objects. All right. So that's the variability part. The last thing I'm going to talk about is kind of fun. This is the astrometry part. And I think it's rather ingenious. So our Earth's atmosphere bends light, right? We have all this air around the surface of the Earth. And when a star shines through it, the atmosphere bends the star. And when you look at a star, you still just see a point. But a telescope with its huge lens and its filters sees the blue star here, a green star here, a red star here, an infrared bit here, the near infrared here, and the infrared here. What's happening is all the light from the star is getting dispersed out into a big band. And since the telescope is looking in one filter, and then another, and then another, and then another, it sees, instead of just a single object, 5 objects that are really close together, that are each in those different bands, but they're actually all the same object. What's just happening is all the water in the air here is just bending all of that light. Okay? Now, astronomers hate this, right? Because you're messing up all their measurements in terms of position, and besides that, they hate the atmosphere in general because it has clouds and things. So generally, we try to avoid looking through the parts of the sky where we have lots of atmosphere.